of unaligned accesses and things like that than even SSE instructions are on the CPU. So it's a good idea if you have the opportunity to build in or update your original host code to deal with padded data structures. That's well worth doing as you begin working on your GPU code.
So are you talking about Intel Larrabees? When you say next generation Intel and AMD will have GPUs on them?
No, it's not Larrabee. So if you've read the news, AMD has a chip called Fusion, which basically has a small GPU on board, and I think Intel has the Core i5 chips, I believe, already have a small GPU on them.
I knew about the Radeons, I didn't know about the Intel ones.
Yeah, and so they both have them, and it's inevitable that those will become more powerful with time. I believe that the state of things now is that those are very low-end, minimalistic GPUs, and a large part of what they do is still emulated in software. But it seems logical to me that over time they will become more capable, and certainly AMD has definitely announced that they will have support for those with their OpenCL. And so if you're mixing, that's another thing to keep in mind. A lot of these algorithms we're working on, they're not strictly for the discrete GPU. You may want to use the same approach or similar approach on both the host and the GPU. So that's something to consider when especially with your data structures, because probably the most invasive change you'll end up making to a legacy code are things that involve manipulating these data structures. So if you're going to have to do it for the benefit of getting the GPU acceleration, you might as well at the same time think about how you can take advantage of the same memory layouts for the purposes of using SSE or these AVX instructions or OpenCL or something like that running on a CPU that has an integrated GPU. So just to give you some example performance results, I don't think they mentioned much of that before. For the older generation, first generation G80, so that's a GeForce 8800, a simple implementation of the direct coolomb summation kernel basically gets 187 gigaflops on a device that is theoretically capable of 330. So that's a pretty good level of performance with a relatively straightforward, optimal single-thread implementation, single lattice point per thread implementation. But we can actually raise that significantly by doing multiple lattice points per thread. And the key thing that was done in this simple implementation is basically, this is a trick you can use in your own kernels too. You can basically cause global memory reads to be stored in a register. So long as you don't touch that register, even though that global memory read is still pending, your kernel will continue executing. So global memory reads do not stall your kernel until the first time that result in that register is actually read or referenced in some way. And so what that means is, if you have a loop like this one, of course GPUs do a wonderful job of hiding latency by having a huge number of threads running on the same hardware. But another thing that they have that's really slick is they have what they call a scoreboard. And when you have a pending memory transaction for your own thread, so long as you don't try to use it, your thread will just keep on running until the first time you actually reference it. And so what we've done here is we've set this register variable current energy to the value that's currently in the lattice. Then we go on and we do a big loop calculating all these potentials, and at the very end we write that per energy plus the new energy out back to the lattice. And because we have organized this so that the load is done early and the reference isn't until the end, this basically allows us to hide our own kernel's latency by doing a bunch of arithmetic. And I've used this trick in probably 15 different kernels, and it works very well. So if you have an opportunity to do some load well earlier than you need it, that can, and especially if you don't have a lot of concurrency, this will give you better performance in the case that you don't have, 100,000 threads to hide your latency. So that's worth mentioning. And you've heard about the loop unrolling before. So basically we're going to have a single thread calculating multiple lattice points using the sum of the partial distance components and the atomic charge multiple times. And the effect of that is we're getting rid of a little bit of arithmetic, but the main thing we're getting rid of are the memory references. So we're basically increasing the arithmetic intensity of that kernel significantly. So that's going from something that was much closer to memory bandwidth bound to becoming close to arithmetic bound, and we've sort of factored out some of the arithmetic operations that are the same between these neighboring lattice points. And so it's a pretty simple kernel. So if we do that, now instead of getting 187 gigaflops, we get 291 out of a possible 330 or so. So that's a very, very high fraction of the machine's theoretical performance for those early GeForce 8800 GPUs. On a GTX 285, the same code gets about 550 gigaflops, and that's a very high fraction of that device's performance too. I think GTX 285 is around 600 gigaflops, 650 gigaflops in single precision. So again, 550 out of 650 is very, very high fraction. And we're achieving that primarily because we've eliminated, by doing all this, you can see there's a lot more arithmetic for each loop iteration, so we don't have much overhead from things like loops. Loops are very costly on the GPU. Just doing those comparison instructions and the branches associated with running that loop. If you have a kernel that has a whole bunch of nested loops, one of the things that you can do to make it faster is to basically unroll several of the loop iterations by hand, so that instead of doing one at a time, you're doing 4 at a time or 8 at a time or something else. And of course, the trade-off that you're making is, in order to do several at a time, you may need more registers to hold temporary variables. So you're consuming that finite resource. So it's a delicate balance. You have to consider how many registers your simplest kernel would use versus how many you use with the unrolled implementation. And so if we do the same thing to a larger degree, doing 8 lattice points at a time, we get something that looks like this. We space out those lattice point indices by the memory coalescing size. We're reusing some of the same distance components several times. So we calculate this once for this thread, and then we get to use it over and over and over and over in each of those potential evaluations. And so that reduces both the arithmetic and the memory references. Yeah.
So how do you understand register pressure? I mean, I heard last week that that don't exceed the register bound. I mean, there's no hard limit, but there's kind of a soft limit.
Well, so what they do is, when you say there's no hard limit, really there is. The GPU has a finite number of registers, and in general, it's, since GPUs use multiplexing hundreds or thousands of threads on the same hardware as a means of hiding latency, there's a trade-off. How many how many thread blocks do I need running on one SM to hide the global memory access latency that goes on while one thread runs? And the answer depends on that ratio of, well, how much of your time is spent doing those memory reads and writes versus how much of your kernel's time is spent doing arithmetic. If you have a very arithmetic-heavy kernel, you don't need to have as many thread blocks running in order to hide latency. You may have so many arithmetic operations that it's easy to hide hundreds of clock cycles of latency. So you don't need to worry about your register use as much if you have a lot of math going on. On the other hand, if you have very little math going on, then the hiding of latency becomes critically important, because you'll be spending a larger fraction of your kernel's time waiting on those memory transactions. There may be more of them pending or outstanding at any given moment, and so anything you can do that will improve that is a good idea. And so if you have for example, if you're doing one of these lattice kernels or stencil kernels where you're doing a small amount of arithmetic and a large amount of memory accesses, those are the kind of kernels that are very sensitive to how many registers you use. If you use more than, on the old hardware, to get 100% GPU occupancy, that's basically the hardware is running the maximum number of threads that are physically possible. You could only use about 10 registers per thread. With the newer hardware, I think you get the same thing with 20 registers per thread, because they have a larger number of registers in the hardware. So it's interesting. That was the trend for the GeForce 8800 generation, and then for the previous generation Tesla, they doubled that register count. For Fermi, the register resources are a little bit more constrained. And another thing about Fermi is it uses 64-bit addressing by default. And so that means everywhere where you have pointers in your code, they're twice the size on Fermi that they used to be for the older devices. And the reason for that is because Fermi GPUs contain as much as 6 gigabytes of memory. And so in order to access that memory, they compile your kernels all the time using 64-bit pointers. And so that's another, when you start designing your kernels and you start looking at where your register consumption is, the number of pointers you're holding on to has an impact on that in a big way, at least on Fermi. And so that's something to keep in mind. So for example, I gave Jim a few suggestions for making the NAMD kernel faster on Fermi, and they would be great, except that some of the suggestions I gave him caused his register use to go through the ceiling, and the register use ended up making the thing slower rather than faster. So these are competing issues, so something to keep in mind.
So what happens if you exceed that limit, that hard limit?
Well, so basically what happens is your register use goes up. The maximum, since you have a fixed pool of registers, that reduces the number of thread blocks that are able to be scheduled at once on the hardware. So you go from something like 8 blocks down to 7, down to 6, 5, 4, 3, 2, 1.
So your occupancy goes down.
And your occupancy goes down, which means your ability to hide global memory latency goes down as well. So instead of having 1 or 2 other threads to hide, thread blocks to hide your latency, you have none, or you only have the warps within your own thread block to help you hide your latency. And they may be doing, since they tend to be somewhat synchronous, they don't help you as much as threads from a different thread block, which can be in a different phase of the calculation. The first time you do a sync threads call within your own thread block, you're causing all your own threads to be at the same point. And so those other warps will only be a few instructions off of your current warp. Whereas a totally different thread block, you can be doing memory reads and writes in one thread block, and the other one can be doing arithmetic, and they'll be somewhat separated by some time there, and so you have better latency hiding behavior then. So the thing that's interesting then is this padding stuff and the size of these thread blocks and the unrolling all sort of play together to affect the efficiency of your kernel for a given data set size. So if we do this thread coarsening and we have one thread compute multiple lattice points, this has the effect of making our computational tile wider or taller or deeper, depending on whether we're dealing with 1 or 2 or 3-dimensional thread blocks. And the other thing that affects is the bigger these tiles are, the more padding elements we might have in the worst case scenario. So imagine if this was a 2x2 grid instead of 3x3, and we had just one element into the next thing, we would have 4 times as much work as approximately as we actually needed. So if we were working on very small problems, having a thread block size this large would be a very bad idea, because the worst case performance would be 25% of the best case performance. So that's something to be aware of. That shows up here. If I compare several of these different CUDA kernels with different degrees of unrolling, so either unrolling by 4 elements or 8